Hi guys, it's your guy Olumide, and today we're gonna be solving one of the most commonly asked tech interview question, the matrix paths ways. It's a DSA problem that's commonly asked by top tech companies including Google, Amazon, Netflix, Meta, Microsoft, Apple, and other top tech companies. The problem statement states that you are positioned at the top left corner of a n by n matrix and can only move downward or rightward through the matrix. Determine the number of unique pathways you can take to reach the bottom right corner of the matrix. So we are giving this example here, example input, whereby the matrix is a n by n matrix of 3 by 3, right? Meaning that 3 rows and 3 columns, right? And we are given an output of 6. The output is going to be 6, right? And what it means is that right from the problem statement, we are positioned at the top left corner of the n by n matrix, which is at this point here, and we can only move downward or rightward, meaning that we are always gonna approach the bottom right corner, because we cannot move to the left and we cannot move away. We can't move upward or to the left. We can only move downward or rightward, right? We have to determine the number of unique pathways we can take to reach the bottom right corner. So looking here, we see that we can take this path, going straight and then down, or we can take this zigzag one, straight down, or we can have this straight down, straight, or we can have it down, straight down. And these are the different paths that we can apply to reach the end. And that's why we have the output of 6, which represents that we have 6 different paths to take that can lead us from the top right to the bottom left of the matrix. Now, to solve this problem, let's think of it backward. Let's think that, okay, we've gotten to the top left, the bottom right corner already. Now we can either get to this bottom right corner from the left cell or from the cell above it. So it's either from the cell to its left or the cell above it, because we can either move downward or rightward through the matrix, just like the problem states, right? So this means that to find the number of paths that we can take to get to any particular cell, then we just need the number of the number of paths to get to its left cell, right? And the number of paths that is needed to get to it, the cell above it, just like we just stated now, right? Because for any cell at all, it actually applies to any cell at all in the matrix. So to find the number of paths to get to that particular cell depends on the number of paths to get to the cell beside it, I mean to its left. Why? Because we can only get there either from the left or from the cell above it, because we can either move rightward or downward, right? So that we approach the very last cell. So, and that way it will definitely depend on those two cells. So, and hence that's why we have this function that to get the number of paths, matrix pathway to a particular cell depends on the matrix pathway to the cell beside it. This actually represents the cell above it, though. This is r minus 1c. So where r represents the rows and c represents the column. So for this particular cell r comma c, r minus 1 means the cell above it, right? That's r minus 1. Why c itself represents that particular column, but the cell above it. Why r comma c minus 1 would represent the same row but the column before it. So, and then this actually represents a recursion relation. And what I mean is that a situation whereby the solution to a main problem, say the problem is finding the number of paths that is required to get us to the top left corner of the matrix. So that particular major solution now depend on some sub problem. So it depends on some sub problem, right? and one of these subproblem is the cell beside it and the cell above it, right? So, and because of that, that's actually I like that we can solve this problem by solving a subproblem. Therefore, we can use DP, the dynamic programming, to solve the problem. So, and the DP relation is just similar to this formula above here, whereby the DP of R comma C, where R comma C will represent the particular position, the row and column position, actually depend on the one before it, which is the one to its left, and the one above it, so the sum of it. So, and that's how we'll be solving this problem. Let's consider the base cases now, because anytime we're dealing with DP, you need to know that we need base cases. So base cases is actually a case whereby we'll be using as a case study, or let me say a reference. So, and then okay, in figuring out the base case in this now, let's consider this particular tree, this particular matrix. Sorry, this is a 4x4 matrix because it has 4 columns and 4 rows. Now you will notice that at the very top left, where we are starting from, right, at the very first cell in the matrix, you will realize that there is only one way to get to that particular part, right? Meaning that okay, probably we are given a 1x1 matrix now, right? So there's definitely just a single way to get to that particular part, because it's actually the only cell in the matrix. So now similarly, because we can only move left and rightward from the left to the right, and move downward, every other cell in this particular first row we only have one path that leads to them, meaning that to get to this particular last row, last column in the first row, is still just one path. There's no additional path to get in there. Why? Because we cannot move upward. We only can move rightward and downward, right? So similarly, this particular column here, the very first column, there's only one way to get there, right? So because we can only move to it downward, we cannot move to it from the left or from the right, and because it is at the very first column, so we can only move it in one direction. So that means that the base case is that we set all of them like this to 1. We don't need to pre-calculate that. We don't need to calculate that again, right? Why? Because they are actually explicit that is only one way that leads to them. So we are going to be setting them to 1, right? So that will be our base case, and definitely that means that whenever I want to start to traverse this board or this matrix, we are going to start from this position, R comma C. Let me put it down. R comma C is equals to 1 comma 1. So meaning that we are starting from the first row and first column, which means this particular position here, this one here, right here, that's where we are starting from. So, and don't forget, why we have to place these base cases is because look at this formula. It actually depends for any particular cell. It depends on the previous cell, right? Meaning that the cell to its left and the cell above it, well, this one that I'm actually pointing at here represent this one here that I highlighted, represent the cell to its top, I mean the cell above it, right? And this one means that the cell to its left. So to prevent an index error, we are going to pre-populate our DP array with 1 1 1 1, knowing fully well that there's only just one way to get to this particular cells at the first column and at the first row. So we're going to pre-populate it with 1 1 1, and after doing that, we are now going to start populating the rest of the DP array. So starting from this particular position, which is the first row and the first column, right? So row of 1 and column of 1 here, right here. So that way now we know that it will always depend on this particular row beside it and this particular row above it. But since they have been pre-populated, that's why it gives us 2 here. So meaning that there are just 2 parts to get to this particular cell, and it gives us 3 here. Why? Because there are 3 parts. So by adding 2 and 1, so and yet give us 4, because by adding 3 and 1, right? So, and that's how we solve this problem. So you see, it's quite easy, right? So we're going to be going to the code implementation now. Okay, let's go into the code implementation for the matrix pathway DSA problem. We'll be defining the function as matrix pathways, right, which correlates with the name of the problem. and then we'll be collecting an integer m and an integer n, which represents the m by n matrix, right? So, and the return is actually what is going to be the number of parts. So total number of parts that will lead to total number of parts that will get us to the bottom right. You understand? That is, that will get us to the very last cell in the matrix. So now we have our parameters here, just like I have in the problem statement, where our m and n are 3 by 3 matrices, right? So first thing now, in solving this problem, we want to define the DP. Don't forget, I actually showed you a board, right, whereby we first of all set all the rows to 0, all the rows to 1, and all the columns to 1. So that is essentially our DP. So it's a table, right, table of solutions, so that we can apply that recurrence function that says that DP of r, or r of c, is equals to DP of r minus 1 of c plus DP of r of c minus 1, meaning that the total number of parts that will get us to the cell before the current cell plus the total number of cell parts that will get us to the cell above the current cell is actually equals to the total number of parts that will get us to the current cell. So to do that, we are going to be defining this table now. So we are going to be setting it to 0, right? So it will be 0 for m in for underscore in range of m. So you might be like, what am I doing? What I'm simply doing is that what I'm simply doing is I want to create that m by n matrix. So, and that's what I'm doing here. So this one that is inside actually will represent the will represent each of the rows. So alright, so I'm gonna do for underscore in range of n, so where m is the row and n is the column. So okay, sorry, this is supposed to be n if n is the column, right? So why this is meant to be the m, since it is the row, and what it's simply doing is that the column will be n if you know, we are actually taking the column to be n and the row to be m for mango, right? And then, so by doing that, now we want the total number of zeros inside the column, inside each of the row, to be n. That's why I say that for underscore in range of n. So, and we want the total number of rows to be n. That's why I say, that's why I put the outside for underscore in range of m. So now doing this, now the next thing I want to do is that I want to iterate through we want to trace through the row, so that for each element in the first row, or for each cell in the first row, we want to set their value to 1, and for each cell in the first column also want to set their value to 1. So doing that for row, for I will say for r in range of m, right? So I'm gonna say that dp of r, so we have pre-populated it to we have actually pre-populated all of them to 0 at first. So we already have it created. The m by n matrix is already created with this dp here, but now I want to set all the elements in the first row to 0, right? So sorry, I'm gonna do that by saying for c, so all column in the first row, right? So I'm gonna set them to 1, because we know that there's only one way of getting to it. So that's why I'm saying that dp of 0 of c, sorry, so it's supposed to be dp of 0 of c, which means that all the column in the very first row, that's why the row remains 0. So similarly for r in range of m, so simplifying that for all the rows in the very first column, so I'm gonna say that dp of r of 0, so indicating that it is the very first column for each and every row. So I'm gonna set them to 1 as well, because what all the cell in the very first column and all the cell in the very first row should actually be 1, because we know definitely those are our best cases, so we know that they are going to be 1. There's only one way of getting to these cells. So now after doing that, now we are going to iterate through for r comma c, for r in range of 2 comma n, right? So what we are doing here is that we want to start from, is it 2? It's supposed to be 1. It's supposed to be 1. So because row are 0 index, right? So we have actually set for 0. So we want to start from the very first row and from the very first column. So for c in range of 1 comma n, right? So that at each point it's gonna start from row 1 and column 1. So it's gonna leave row 0 and column 0 alone. It's going to go and start from row 1 and column 1, then row 1 and column 2, and on like that. So, and what we want to do is that I want to set the dp of r of c, so of each of this row, to dp of r minus 1 of c plus dp of c of r and c minus 1. So this is simply what we want to do. So meaning that it's going to set the paths, the number of paths to get to the current cell to be equals to number of paths to get to the previous cell to the left and one to the top of it. So, and after doing that, we just want to return dp of r of m minus 1 cm n minus 1. So, and what this simply means is that n minus 1 will refer to the very last column in the matrix, where m is actually 3 and it is 0 index. So n minus 1 is going to refer to the very last row, while n minus 1 is going to refer to the very last column, right? So both of them definitely will refer to the very last cell in the matrix, and then we just want to return the number of paths that is going to get us to this very last cell. Don't forget that from the problem statement, it tells us that we are moving from the top right to the left bottom, and we want to find number of paths that will get us to that left bottom. So, and then this dp of n minus 1 really represents the number of paths that will get us to that left bottom. So let's run this code and see how it goes. Here it is, we have 6 returned, which is actually correct, right? So, and this is how to solve this problem. So yeah, there are 6. If you go look at the problem statement, you find out that it is also 6. So this is how to solve this problem, and I really hope you do understand. If you do, kindly like, subscribe, and comment on my YouTube channel. Do subscribe, please. Thank you so much.